Good afternoon, everyone, and welcome to the Theory, Water Activity, and Microbial Growth. My name is Orna, and I will be your host today. A few words about Neutec. We are a market leader in implementation of innovative technologies in the Quality Control and Research and Development Laboratory. Our goal is to help you, our customers, improve your laboratory workflow, your productivity and efficiency, and hopefully consequently your results. We do this by providing access to a broad selection of quality instrument solutions manufactured by our strategic partners. Related to our presentation today, we offer cutting-edge instrumentation solutions for both the microbial challenge testing and water activity testing. Today you're going to hear from our Senior Applications Scientist, Dr. Brady Carter. This would be our third webinar with Dr. Brady. Hi, Brady.
Hello, I'm here.
Hi. Dr. Carter specializes in water activity and moisture sorption applications. He earned his PhD and master's degree in food engineering and crop science from Washington State University. Dr. Carter has 20 years of experience in research and development and has been the instructor for water activity seminars in over 23 different countries and has provided on-site water activity training and quality control consultations for companies around the world. He has authored over 20 white papers on water activity, moisture sorption, isotherms, and complete moisture analysis. He has participated in the hundreds of extension presentations and has given talks at numerous scientific conferences. You're all going to receive a copy of the presentation, so there's no need for you to keep up with taking notes. We plan on having some time for Q&A towards the end of the presentation. If you have any questions, please click on the icon at the bottom of the screen and just write your questions in. Make sure you're choosing Neutec Group Host, NG Host. And we hope to have enough time to answer. If not, we're always available. One last thing before I pass the presentation over to Dr. Carter. At the end of the presentation, we're going to be posting a link to a short survey in the chat bar. Please take just a short moment to complete it. We really want your feedback so that we can continue to speak about the topics that you care about. On this note, I'm going to transfer the presentation to Dr. Carter.
Great, thank you, Orna, and thank you everybody for being here today and to join us in this webinar. Hopefully, it will be a useful time for you, and that you'll be able to learn some new things possibly about this topic of microbial growth and water activity. But to start off with, I want to just quickly go over some concepts and principles associated with microbial safety. And this will be applicable, obviously, to anybody who makes a manufactured product especially that's going to be consumed, because the safety and the lack of or removal of microbial organisms that can result in infections and sickness is of highest priority for making these types of products. And when we talk about microbial safety, we can kind of break that risk into two main groups, and how the microorganisms have the highest probability of being able to cause problems. And one of those is through microbial contamination, and the other is through microbial growth. Microbial contamination mostly deals with production and actually making the product, and whether or not the production process itself, whether that be from incoming ingredients or from handling of product or the production process itself. In these situations, there's always the possibility of there being the introduction of microorganisms, and that if those microorganisms are present in high enough concentrations to result in an infection, then they will potentially get somebody sick, and that product would be deemed unsafe. And so that's obviously a very high risk. And in order to prevent that from happening, the preventative controls that are used are typically that there is some type of a kill step that the product may go through. That could be through heat or pressure. It also is prevented by good manufacturing practices, or GMPs, where you make sure that your facility is clean and it's kept and maintained clean, and is that you have routine cleaning steps that are applied to the production facility and meeting those requirements. And again, these efforts are to prevent inoculation of your product, as well as kill anything that may be present on the product. And so the way to monitor this, to make sure that it's effective, whether it be the kill step or whether it be your good manufacturing practices, the way to monitor this is typically through microbial challenge testing, where you either do an assessment to just try to see if there's microorganisms present, or you may even do a specified test to try and find a particular organism. In terms of microbial growth, this is something that typically happens after the product is made or manufactured, where you may make the product to and using good manufacturing practices, and you have a kill step, and all that goes well. But what happens to the product once it's produced, and it goes into the package, and it goes into transport, and it gets stored in a warehouse, and it gets put on a store shelf, and it goes to the consumer? And all during that time, there is still the possibility that microorganisms could grow on the food product itself to high enough levels to cause an infection. And so they have to be, if they're in a situation where that could potentially happen, then there needs to be some other ways or prevention steps taken to prevent that from happening. So one of the best preventative controls for keeping microorganisms from growing on the product itself is through the reduction of water activity. And that's what we're going to really focus on today, is how does that actually work? How does water activity actually keep microorganisms from growing? And there are other factors that can prevent microbial growth as well. We'll talk briefly about those, but again, focus mostly on water activity. So the preventative control in this case, and the one that we're going to focus on, is to manufacture the product to water activity levels that make it safe from microbial growth, whether that be from mold growth or from pathogenic bacteria. And so the way that you monitor that, so that's your preventative control, the way you monitor that is through water activity testing, using water activity instrumentation. And then you set some sort of a specification based on where that product's going to be safe, and then you're going to routinely check that through water activity testing. So in terms of solutions for monitoring, what are available? What can you use, whether you're talking about the monitoring tool being microbial challenge testing, or whether you're talking about the monitoring tool being water activity testing? The first one for microbial contamination, the second for microbial growth. In terms of microbial challenge testing, there are ways to make that process easier, less laborious, less time consuming. And that's typically through the use of automation, whether that be from automation on your media preparation and plating, creating the plates for doing the testing, or through automated dilution to make sure your dilutions are correct and easily done, and mixing, or to automate the inoculation process and then the colony counting afterwards. Solutions in terms of water activity testing, of course, the main solution there is a water activity instrument. But that water activity instrument, in order to be able to be an effective monitoring tool and meet the requirements of regulations, whether that be HACCP regulations, HARPSIA regulations, drug release regulations, that needs to have some specific, the water activity instrumentation needs to have some specific characteristics to make it effective and applicable. One of those is temperature control, because water activity is temperature dependent. So it's important to have that temperature control in the instrument. You want an instrument that's stable with low maintenance, so that you're not having to constantly clean it and adjust it and check it, and that it has an easy verification process, because one of the key parts of both HACCP and HARPSI plans is that you have a way of verifying your monitoring tool. And that's so it's important that your water activity testing instrumentation can be verified easily and without it resulting in a large amount of cost for you. Now, in terms of Neutec Group, who's obviously this is sponsoring this seminar and who I work with, in terms of the solutions that they are able to provide both solutions for microbial challenge testing as well as solutions for water activity, and that's what this diagram is showing. And encircled is those tools that deal with microbial contaminant or challenge testing automation, and at the top and then at the bottom left corner is the water activity instrumentation. So again, Neutec is able to provide solutions, whether that be in terms of microbial challenge testing, whether that be in preparation of media, or whether that's in actual checking of the sample. So just real quick to cover, if you're doing microbial challenge testing and different types of microbial testing, and you are interested in automating that process, making it easier, it's taking a lot of time. I just really want to real quick highlight some of those tools that are provided by Neutec Group. And then if you're interested, let us know. We can provide you with additional information and possibly have a seminar that's focused on talking about just these types of solutions. But real quick, one of the things that folks who do testing of microorganisms, one of the things that a trend that's been is to try and bring that media preparation in-house and make it effective, especially if you want to do any kind of selective testing for microorganisms. That's much easier done if you're able to adjust that in-house. And so one of the solutions that we provide is automation of media preparation. And there are several different options, as you can see listed, and that's from autoclaving, pumping, to plating itself. And even we have an XY tube and bottle filler where you can it basically tell it where each of those bottles are and what to put in there, and it will dispense those automatically. I also offer both linear and linear types of media fillers, and also ones that have carousel. We feature both types. So there are plenty of options. If that's something that you're interested, please contact us. And then on the other side, after the media is prepped, then of course you have to actually inoculate it to make it so that you can determine whether microorganisms are there. And we offer automation options for this as well, including spiral plating for inoculation. The EdiJet that's shown here does a spiral plate, which the advantage there is that you achieve a 3 to 4-fold dilution right on that plate itself, so it doesn't require multiple plates in order to achieve the dilution. And then we also offer automated colony counting options to then take when those colonies have grown, and you can separate them using this colony counter by colony type, or just simply do an overall count. So there's options there for automating that whole process. And again, if you're interested, please let us know. Now, in terms of water activity, and water activity as it applies to microbial safety, let's talk a little bit about how to make water activity work for you. How would you implement water activity if you haven't, or maybe how might you best use or further utilize your water activity measurements? And keep in mind that during this seminar, we're talking about water activity and its relationship to microbial safety. Water activity is also related to chemical stability as well as physical stability, and those will be additional webinars that will be coming up. So this is in particular is dealing with microbial, the risk of microbial growth, but we'll talk about the other things water activity can affect as well later on. Now, the way to implement water activity in a food safety program or a drug safety program, whatever it is that you work with, is the key first element is to implement water activity as a preventative control in whatever plan you create, whether that's a HACCP plan, whether that's a HARPC plan, or whether that's a drug release program. But water activity under all of these different types of paradigms is a valid preventative control and is actually identified as a valid preventative control, whether you're talking about guidelines for HACCP, guidelines for HARPC, or guidelines through ICH or quality by design for drug release. And so as a preventative control, one of the things that you have to do is identify which microorganisms pose the greatest risk. This is that risk assessment that's a critical part of making that plan. And then once you know what those organisms are, then you can identify whether or not your target water activity for your product is going to prevent those organisms that are of greatest risk by comparing it to some growth limit tables that I'll show you later. And then you got to outline a plan of how you're going to monitor that and make sure that your product never exceeds whatever that target is, so that you can assure the safety of your product down the road. And that includes the possibility of temperature abuse and other things that could happen have to be factored into that. And then, of course, you have to describe the verification process for that water activity instrument that you're going to use to ensure that it's giving you good quality data. So what is water activity and why does it prevent the growth of microorganisms? So if you've been in any of our other webinars, you've probably already seen our description of water activity and heard me define that. But real quick, in case you haven't, or if you need a refresher, water activity is a measure of the energy status of water in a system. It's not the amount of free or available or bound water. It has nothing to do actually with available water for microbial growth. The reason why it has an impact on microbial growth is because of its relationship to the energy of water. And we'll talk about that whole mode of action in just a minute. But critical again, water activity is the energy status of the water in the system. It's telling us what is that energy relative to the energy of pure water. And so the way that that's determined practically is we take the partial pressure of water above a sample at a certain temperature and divide it by the saturated vapor pressure or the vapor pressure of pure water at that same temperature. And this is the same way that you determine relative humidity, partial pressure divided by saturated pressure. But in this case, we're talking about equilibrium conditions, so that's equilibrium relative humidity. But that's the same thing as water activity if you just divide by 100. So again, keep this in mind as we talk about why water activity impacts microbial growth. Now, in terms of the introductory work, pioneering work that was done in order to start linking up water activity to the growth of microorganisms and even beyond that to what are those actual limits, what are those growth limits for each type of organism. And that all started with work done back in the 1950s by a man named Dr. Scott, who was working in Australia. And his work, and it was inspired by this fact that you could have two different products that have the same moisture content or amount of moisture, and one would spoil and one would not. So it was obvious that the amount of water that was present wasn't having any impact on whether or not microorganisms would grow. And so his work was to focus instead of on moisture content, then instead on water activity, which was a known concept at that time of being the energy of water related to that chemical potential energy through the laws of thermodynamics. And so it actually made sense too that what's actually determining whether organisms grow is the energy of the water, not how much water is present. And that's what's going to dictate whether the organism can utilize that water that's present. So if we take that information, we can break down by organism type the water activity growth limits for each of the different major groups of microorganisms that pose a threat for product safety, whether that's food or pharmaceuticals or whatever manufactured product. So the first key breakoff is at 0.91, where all gram-negative bacteria stop growing. So below 0.91, there are no gram-negative bacteria that can grow. Below 0.86, the gram-positive stop. 0.88, the practical limit for yeasts. 0.80, all mycotoxin production stops. 0.70, the practical limit for molds. And then at 0.6 is the absolute limit for all growth. So there are, the reason why we use these terms practical limit for yeast and molds is there are some xerophilic molds and osmophilic yeast that can grow below 0.7 water activity, but they're fairly rare and they aren't common spoilage organisms. So the practical limit is at a higher value where you're essentially, if you're below that, the odds are you're not going to encounter any types of molds or yeast that can grow if you're below 0.7. Now, in terms of actual organisms themselves, specific species, where do those cut off? We can create a chart and show where those growth limits are for each individual species of pathogenic bacteria. So that's what this is showing. You can see here the E. coli shown at 0.95. You can see Salmonella there at 0.95, Listeria at 0.92, and then Staph aureus that grows lowest at 0.86 when you have oxygen present. So these represent the growth limits. Now, what's critical to understand here is that these values represent kind of worst case scenario where all other factors for growth for microorganisms are at optimal levels. So for instance, the pH and the temperature, two other things, major factors that affect whether a microorganism can grow are at optimum. And in addition, there's not a limited nutrient source for the organism. So all types of things that could impact its growth are set to optimal conditions. So the only thing that's being changed is the water activity. So this represents the minimum water activity where these organisms will grow when everything else is perfect for their growth. So what you'll find is that if you change those other factors like pH or temperature, the water activity level where these organisms will grow will change, or will stop growing, will change. So where Listeria, for instance, will grow down to 0.92 when everything else is great, if you lower the pH, then Listeria may not grow at any water activity, because if you get below 4.2, it can't grow. So these values represent when everything else is perfect, the organisms will not grow at water activities less than this. So if you really want to be safe, no matter what else is happening, these are the values that need to be targeted. Now, this table shows this actually working in real food matrices. So not just on standard systems or on a media plate, but actually in particular food products. And we can see that these growth limits that we've identified are applying in real conditions. So, for instance, in sweetened condensed milk, below 0.85, you have an inhibition of Staph aureus, but in a cream filling at 9.7, growth and toxin production. Where you have a meat and cheese at 0.90, you have growth, but at 8.4, below that critical level in dried beef, inhibition. You move to some other types down to the botulinums, where you have you have no toxin when you get down to water activities below in the 0.93 range, but if you get up above that to 0.96 in a pasta, then you start to see toxin formation. So this actually works in real types of food systems, these rules in terms of where these minimum growth levels apply. Now, if we move on to molds, here you see listed the common spoilage organisms in the Aspergillus and Penicillium genuses. Each species within there you can see has a particular place where they stop growing. And that lowest one down there at 0.7, we call that the practical limit, because just below that species is a xerophilic mold that is rare and not a typical spoilage organism. So that one does appear below 0.7, but all the rest are at 0.7 or higher, so that's why we call 0.7 the practical limit. In terms of yeast growth, we can see again the common spoilage organisms, the Saccharomyces family or genus there, and you can see all those stop growing at 0.8, actually quite a bit high or than the molds, but there is an osmophilic yeast that will grow down to 0.62. But again, we identify that 0.80 as the practical limit for yeast if they are going to be an organism that could potentially grow. Now let's spend a little time and talk about what the mode of action is of water activity and how it prevents growth. If we take and we consider a microorganism in its simplest form is a semipermeable membrane that surrounds a sac of solute, essentially, where in the interior of that organism, there is in that environment a certain water activity maintained by the organism. And in order for that organism to be able to go through its required metabolism and steps for reproduction to grow, it has to have that optimal condition in its interior, that optimal water activity. When it encounters an environment whose water activity is lower than its internal water activity, such as at 0.90 shown on the figure, then water starts to move out of the cell. Why? Because water moves from high energy to low energy. That's dictated by thermodynamics. So again, back to this idea that water activity isn't a measure of the available water for organisms. It's a measure of the energy of water, which happens to be related to the growth of organisms because of those differences in energies. Because water will move from high to low energy. So as water moves out of the organism, because it's in an environment whose energy is lower, or where the water's energy is lower, then as a consequence of that, it of course loses turgor pressure as that water is lost. And that having a critical turgor pressure a specific turgor pressure is critical for normal actions for the organism, metabolism, and so forth. So when that turgor pressure is lost, that microorganism stops functioning essentially, and won't grow at that point, and can't do the things that it needs to do. And so as a response, it tries to lower its internal water activity to try and get it lower than the water activity of the surrounding environment, so that water will start preferentially moving from its environment or from the environment around it back into the cell to be able to build that turgor pressure up. And so the way that it lowers its internal water activity is kind of the same way that we lower water activity of foods, through the use of sugar, salts, humectants. It concentrates those in its interior in an attempt to try and lower the water activity. And again, it's trying to get lower than the surroundings. Each organism has its own unique ability to do this, and that's why there are differences in growth limits. That those tables that we showed previously, the reason that those numbers are where they are for each of the different species is a reflection of how well and capable they are at responding to osmotic stress. How low can they get their interior water activity such that they can start bringing water in from the environment? If in their efforts to do that, they still can't get less than the environment, then they have to go into a dormancy stage, where there's no growth, they aren't actively reproducing, but they still are present. And that's a really important key aspect of this mode of action, is that water activity is a preventative tool for growth. It prevents growth because of this relationship between energies of water inside and outside. It does not kill. That process of desiccation of the cell doesn't necessarily kill it. So water activity should not be considered a kill step. In fact, many different organisms can survive for a long time at low water activity conditions. Now, if we take a look at a growth chart, this is a logarithmic growth chart where we're seeing log growth levels here on the y-axis. As you change the water activity, and this is for Staph aureus, you'll notice at high water activities, the growth curve has a very steep slope, and the stationary phase is at a very high water activity, such that the counts are high enough levels to cause an infection. But as you lower the water activity, you see slight differences and changes due to that osmotic stress, and eventually you'll get it low enough where that growth curve's slope has been reduced significantly, such that the stationary value is now you have a fourfold log reduction in growth, such that at this level now, that's not high enough levels to cause an infection. So that reduction in water activity has slowed the growth enough to the point where you're not going to have enough growth in there that somebody were to eat that product that they would get sick. So in terms of survival of organisms at low water activity and why is that important? Well, of course, one key thing is that you should never consider water activity reduction as a kill step in your food safety plan. But in addition, it requires some consideration, especially when it comes to ingredients, because a lot of the low moisture ingredients that are provided for the manufacturing of products have the potential at that low water activity to still have organisms present, because they typically will not go through any kind of pasteurization process. If they come in and they're put into a product who still has low water activity, or they go through an additional kill step as part of the processing, there may not be a problem. But if not, when those ingredients are added and they have surviving, for instance, salmonella in peanut butter or chocolate or flour, and they come into an environment where now they're in a recipe whose water activity may be quite high, the problem is that those organisms now in an environment where the water activity is optimal will start to grow again. And so these low moisture, low water activity ingredients can potentially be the inoculation source for problems. Sometimes they just have enough in them where the product itself has enough inoculant to get someone sick. And that happened in the case of peanut butter and the recall on peanut butter some time ago that's quite famous. But even in these things like flour or powdered milk, they get added, water activity goes up, the organisms start to grow, and say they're put into some type of a bar, and there isn't necessarily a pasteurization process. So it's something to be aware of. Because of this risk, there is a stipulation in FSMA now that's going to potentially require all manufacturers of low moisture ingredients to show pasteurization and have to pasteurize these ingredients. And that's not easy to do because they're low water activity. So that's a challenge in of itself, and something I'm working with a group on that are trying to optimize that process, because water activity, even in those low moisture ingredients, plays a critical role in how effective the pasteurization process can be. Now, in terms of microbial growth and its relationship to water activity, it is possible to model what that effect is in terms of rates of growth. So if it's something that you're interested in trying to model microbial growth rates for a given product, it is possible to model that. These models have to incorporate not only water activity, but other factors that impact its survival and growth. So, for instance, temperature and pH being another two that play a critical role. These models are typically just empirical, derived for a particular case, but they relate the response to each of the different control factors being changed to how or what that rate of growth is. So an example of how this type of an experiment might be set up, this is taken from Cindy Stewart's paper from 2010 where they did some of this modeling work. So it's given as an example. This isn't necessarily going to fit perfectly with something you might want to do, but it's meant to be a guide, where they created different pH values through addition of hydrochloric acid, and then they produced different water activities through the use of humectants to lower or change that water activity. And they had the presence or no presence of a preservative, used Staph aureus, used a bioscreen system to look for optical density to detect when growth had happened, and set this up as a replicated experiment. And what they were able to do from that, from the time series data they collected, was create some multivariate, or do a multivariate analysis and create models that showed the best capability of being able to predict the change in rate of growth by putting in these factors. RH in these models represents water activity. pH, of course, is pH. The sorb represents whether or not there was a preservative present. And so what these models are empirically driven, multivariate models that could be used then to predict what the rate of growth would be depending on whatever the factors are that you put in. Is there a preservative? Is there not? What is the pH and what is the water activity? And notice that the models actually are specific to the type of humectants that were used. But what you can get from this, if you go through and create these models, is a tool where you can basically put in conditions. Again, %RH here is water activity. So at 0.92 water activity, pH of 7, and no preservative, growth is predicted from those models to happen in 1.7 days. And essentially the idea here is growth is not acceptable. So however long it takes to have growth is essentially the shelf life. And so this fails because it's only 1.7 days. However, if you change the water activity down to 0.87, where it was at, where the pH doesn't change and there's still no preservative, under these conditions, now you can have almost 1,100 days before you're going to have growth, what's assessed as enough organisms to represent growth. And so that, of course, would be safe or would pass. And so this is something that is possible to do, to try and do some predictive modeling. These particular equations that I showed you, again, were empirically derived specific for this situation. This isn't a case where you could take those and plug them in for your product, but instead these are meant to be principles, to show principles of how you could potentially do this if you're interested in doing so. Now, in terms of microbial failures, the consequence of microbial failures, of course, can be huge, not only because you get somebody sick and there's the potential for even death under those situations, but in addition, there can be other long-term consequences, most specifically damage to the brand, where now there's a reputation that product had a recall, and they relate then to other products under that brand name as being suspect, and so of course that reputation can be very damaging. In terms of just the impact of foodborne illnesses, you can take a look here of how often that happens. 76 million illnesses, even 5,000 deaths annually that are due to problems with foodborne pathogens. So obviously it's important to prevent this and limit it, and that can be done through what we've been talking about with control from water activity. Now again, water activity is not the only factor that affects microbial growth. There are others. These different factors, though, tend to work together synergistically. We call them hurdles. And this is called hurdle technology, where the idea is that if you put enough of these growth factors, if you limit them and enough of them, that you can prevent microbial growth at levels that in of themselves for those particular growth factors may not be effective. And to show that, you can see here in case number 3, where water activity presented as a hurdle for this particular organism is enough. It prevents growth. So in this case, only water activity control would be necessary. But at that same water activity for another organism, it may be able to overcome that. But if you combine the effect of water activity with pH, and in other words, you put that many hurdles in front of the organism, it can't get past that and it can't grow. And so you can have effective growth or effective prevention at levels of these factors that in and of themselves, if they were the only factor, would not be able to provide the kind of or the protection that you would need. And this is even reflected in the definition for potentially hazardous foods, as you would find in the food code. In the food code, these definitions include a couple of tables, and this first table is table A, which is for a situation where you have a product that you have a kill step and destroy vegetative cells, and then you package. So this would be anything that's cooked, baked, and then put in a package. Under those circumstances, you only need to have a water activity of 0.92 or less to be considered completely safe. And that's because only spore formers can survive those types of conditions. If you have a pH of 4.6 or less, you're considered safe. But notice you can be even higher than 9.2 and higher than 4.6. But if you're a little bit lower in pH and a little bit lower in water activity, you're still safe, even though this is higher than the value that would be needed to be safe if only water activity were the factor. In another table, in table B, this is for a situation where you don't have a kill step, or once your product's out of the package, because once it's taken out of the package, it's now exposed to different kinds of conditions, and it can assure that that pasteurization process is still there. So in this case, you got to be below 0.88 to be considered non-potentially hazardous, or below 4.2 in terms of pH. But again, notice that there are cells in here where you have a higher water activity and a higher pH, but because they work together synergistically, you still prevent growth. Anywhere where it says PA in here means you have to prove, if you're not going to provide a temperature as a means of control. So you don't have, if you're not going to use time temperature control, you have to do something else to prove that your product is okay at those pH and water activity levels, or you refrigerate it. So in terms of government compliance, water activity shows up as a critical parameter in many different areas. I just showed you in the definition of potentially hazardous foods. In terms of the Food Safety Modernization Act, it is it's found in the HARPSI plans as a way of being able to, or a preventative control. In USDA, if you deal with meat or eggs that are handled under the USDA, then you use a HACCP plan, where it has critical control points, and water activity is considered one of those critical points. If you deal with pharma, USP method 1112 represents a way to be able to justify the use of water activity. And then if you deal with cosmetics, there's an ISO standard for how to control microbial growth using water activity in cosmetics. So looking a little bit closer at regulations for human and animal food handled under the FDA, under these new FSMA guidelines, this is a risk-based approach. So you create a HARPSI plan that identifies your risks. What are the preventative controls that are going to prevent those risks? How are you going to monitor that? And then how are you going to verify it? And that includes water activity as one of those viable tools. In terms of cannabis, this is an up-and-coming product. If you deal with cannabis, water activity shows up in regulations for cannabis as well. You can see several of the states represented there and where water activity shows up. So certainly it's an critical part of this kind of new market of handling product, where preventing microbial growth is incredibly important from a safety standpoint, but not just pathogenic bacteria like in the foods. In this case, molds can be really dangerous in these types of products. So it's critical to have them to an appropriate water activity. Again, keeping in mind that the same tables apply in terms of growth limits, whether you're talking about cannabis or you're talking about food or you're talking about pharmaceuticals. Now, with pharmaceuticals, there exists a USP chapter 1112 that talks about the use of water activity in pharmaceutical products. And being able to use water activity as a justification for reduced microbial challenge testing or limits testing in products that are just very low water activity and have no capability of supporting growth. So this is playing a more important role now in pharma than it maybe it used to. And coming soon will be a chapter specific to water activity and its measurement for those of you that are in the pharma industry. Now, water activity then, due to its relationship to microbial growth, as well as other factors that affect shelf life that we'll talk about in other webinars. But the idea here is that if you identify a ideal water activity for your product that's going to keep it safe, prevent growth, then that's what you should process to, and that's what you should release on. And under processing could make it dangerous, but over processing isn't necessarily a good thing either. And so it's important to monitor water activity and test it as frequently as you can to track what's happening in production process to make sure it's meeting that requirement, with the understanding of that and the setup of that ideal water activity based on many factors that could happen, like abuse afterwards. And we're going to talk about packaging and what role that plays in another webinar as well, and how water activity changes in the package. But the idea here is you identify your ideal water activity and then you process to that. And over processing to, as you can see in this graph, if you identify 0.7 as the ideal water activity, over processing it to a much lower water activity doesn't make it any safer from a microbial standpoint. But in the process, you've lost 5% of your product due to removal of water, the cheapest ingredient there is. And in fact, when you lower water activity, sometimes you can make other problems like texture problems or even chemical stability problems that don't deal with necessarily microbial safety, but are still important for the shelf life of the product. So, and you'll see this show up in most of our webinars, this idea of why water activity is such an effective specification for production, because it allows you to optimize your product, optimize its weight so that you're optimizing your revenue. Now, in terms of solutions for water activity measurement that are provided by Neutec, this is just a quick table showing the different options. The LabMaster Neo is the top of the line, highest level of accuracy, highest effectiveness for temperature control, least amount of maintenance, most features available. And you can see that it can be used for any kind of product. And then as you move down to the lower, again, lower cost, but less features, less lower accuracy. But there are those different types of options that are available, and that's there for your reference. But just in terms of the advantages of Neutec water activity meters, they provide meters that are manufactured in Switzerland by a company named Novacina. The meters that are available, they have the highest accuracy available in depending on the model. Another great advantage of water activity coming from Neutec is that these systems utilize reusable saturated slurries for their verification process. So these aren't consumables, as is the case in other for other manufacturers who make standards that are one-time use. And so these don't have to be repurchased. They have a 3-year shelf life and can be used over and over again. The electrolyte sensor that's utilized in the Novacina instruments is very stable and almost maintenance-free. These instruments don't have to be constantly cleaned to keep them reading correctly, and because of that, they don't have to be verified as frequently. There also is the possibility of putting in filters. So if you make anything with volatiles that can interfere with water activity readings for most types of measurements that are out there, for the systems that are provided, there is a way to put filters in that keep those volatiles out so that you're still able to take a water activity measurement using the same sensor. You just put in the filter that's needed for that product or for that volatile that could be a problem. These systems allow you to change the test requirements that have to be met in order to end the test. That means that you can get quick results, but you can also set those more stringent to get true equilibrium results. And that's one of the key factors for water activity is getting true vapor equilibrium. And I talk about that more in other webinars and videos if you're interested in learning more about what that means. And of course, they do have temperature control, and they have a whole range of different options from depending on what you're looking at and looking for. Now, in terms of future water activity webinars that we're planning, again, we're going to talk next time about water activity and chemical reactions and how water activity impacts the reaction rate of degradative reactions such as lipid oxidation and browning. We're also going to talk in the future about physical stability in water activity and how water activity is impacted by packaging and how you can predict what will happen in a package to the water activity of your product. And with that, that's our webinar for today. I hope it's been enjoyable and helpful for you, and you've learned something. And now we have a little bit of time, I think, to take some questions.
Thank you, Brady. That was great. We have a few questions already. The first one being, is there a certain temperature we should be testing at for RTE seafood products?
So the typical temperature for measuring water activity, as outlined in most standard methods that are available and out there, is at 25 degrees C, and that's what's considered room temperature. You may find that it's a little bit warmer than most people's room temperature, but but it's kind of the accepted value. That's typically where you would take your measurements, and the instruments, again, that are temperature controlled, they typically will default to that 25 degrees C so that your tests are always running at that value. And that's, again, why it's so critical to have temperature control in your instruments, because if you set up your program to run water activity at 25 C in this case, for your ready to eat seafood, and then throughout the year, your lab conditions change with the seasons so that you don't have temperature control on your water activity instrument, then it's going to be reading at, say, 22, or maybe sometimes during the year at 27. And so that's not going to give consistent results. And especially for auditing purposes, if you can't show that that's at a constant temperature, then it's impossible to be able to do comparisons across the year. So typically that's the temperature you want to use, and you want to have temperature control so that you can assure that you're always testing at the same temperature. And in fact, when you test water activity, it always has to be reported with the temperature. So if you're recording results in a log book, or you're doing them on the computer, make sure that you always report the temperature. And this is not the set temperature, but the actual temperature that's given on the screen for the water activity, that you report that as well. Because again, if I were to take a look at a water activity test and I don't know what temperature it was run at, I can't repeat it. So it always has to be accompanied by a temperature. Now, there are situations where you don't want to read at 25 C, and that's if you want to check for abuse conditions. So while you might do your routine tests at 25, it is a good idea to at least check your product at higher temperatures, like say at 35 or 40 C, to see if the water activity increases, which it typically does with temperature, but not always, and it's very unique to each product. But then you can check whether at that higher temperatures, in case they were to experience abuse conditions, would the water activity move high enough to then cause a problem, where maybe it's for instance, it's at 0.81 at 25 degrees C, but at 40 C, it's at 0.89, and now you have the potential for staph to grow on that product. So keep that in mind. It's not something, again, you need to do routinely, but you should, when you set your water activity specification, it should be set such that even if it were to encounter 40 degrees C, it would still be under the growth limit for those organisms. So setting it right at 0.87 at 25 C may not be the best option or the best idea, because is it still going to be there if you're at 40 C? And again, the way to best check that is to have instruments that can increase temperature. So not just at 25 C, but also tested at 35 or 40 C. And the instruments that are provided by Neutec, at least the Lab Touch and the Lab Master Neo, have the capability of being able to increase that temperature, so you can check that.
Thank you, Brady. How does particle size and surface area affect water activity?
So in terms of them as just physical characteristics, if you were to read the same matrix at two different particle sizes, is not going to change the water activity. So for instance, if you were to take a solid product and put it in a mortar and pestle and break it down into large pieces and then break it down into small pieces, assuming that there aren't other factors like the relative humidity of the room and your length of exposure, it's not going to change the water activity. What it will change is the time that it takes to get to vapor equilibrium. And so that's where the surface area becomes important. So increasing the surface area by crushing is, in a lot of cases, is very helpful in being able to speed up the test by speeding up the vapor equilibrium process. Because the higher that surface area and the higher the surfaces that it has in order for that water to escape and get into the vapor phase, the faster that testing can be. So that's something to keep in mind. Again, you have to, during the time when you're processing it or putting it into smaller particle sizes, every amount of time that it's exposed to the room, thinking back to the idea that relative humidity and water activity are related, then if you have a product at low water activity in a room that's at high humidity, all the time that it's exposed, it's absorbing moisture and changing its water activity. So it's something to keep in mind. You want to minimize the exposure time when you're doing that kind of processing.
Brady, our last question for today, someone's asking you to discuss measurement of moisture content. They're saying we have to correct our analytical results to 0% and 12% water.
So it doesn't make a lot of sense to do that in terms of water activity, because what you're interested in is what the water activity is of your product as it's manufactured. That does make sense for other types of tests to standardize on a specific moisture content, but it's not something that you would necessarily want to do in terms of water activity. You can alter the water activity and predict what that alteration would be based on a change in moisture level through something called the moisture absorption isotherm, but it's not something you would typically do when reporting water activity. Instead, you want the water activity of your product in the condition that it's going to be released or sold, because you're not dealing with a relative value to the amount of water that's present. You're dealing with what is the energy of water of your product at its condition and the amount of water that's present in that product when it's going to be released.
Thank you so much, Brady. I think we're at the end of our time. Thank you, everyone, for joining us today. If you still have additional questions, please feel free to email us at info@newtechgroup.com. Before we wrap up, please check the chat box for the survey link, and let us know if you'd like someone from our team to reach out to you. Thanks again for joining us. We hope to see you in future webinars. Enjoy the rest of your afternoon.